Section: Introduction. In this section, we delve into how the selection of a sequence mixer, such as attention or convolution, plays a crucial role in determining the performance and efficiency of a language model. Previous studies have highlighted that attention mechanisms are particularly adept at recall, meaning they're good at referencing back to earlier parts of the text. However, models based on attention face challenges during training due to their high computational demands, which grow significantly with the length of the sequence. This also leads to substantial memory usage during the model's operation. This raises an important question. Is it possible to enhance the speed and reduce the memory requirements of language models without sacrificing their quality? Recent advancements have introduced several architectures that promise significantly better performance in terms of speed, while maintaining a level of quality comparable to attention mechanisms, as measured by perplexity. Yet, relying solely on perplexity as a measure can hide critical differences in the quality of models. For instance, it has been found that gated convolutions, despite their less than quadratic complexity increase with sequence length, do not match the efficiency of attention mechanisms in recall tasks. Building on this insight, we have conducted a comprehensive evaluation of various architectures on tasks that require intensive recall capabilities. Our findings reveal that attention mechanisms outperform the best non-attention alternative, known as Mamba, by a significant margin in terms of accuracy. This discovery led us to investigate the trade-off between models that excel in recall and those that offer high throughput. We examined a variety of architectures, including attention, state space models, SSMs, and convolutions, on a well-known synthetic associative recall task. By adjusting model parameters that influence the size of the model's memory during generation, we identified a fundamental trade-off between recall capabilities and memory usage that applies across different types of architectures. Attention mechanisms achieve perfect performance on associative recall tasks, but the size of their memory, specifically the key value cache, increases linearly with the length of the sequence. We explored the possibility of using sliding window attention to limit the memory size, although this approach compromises the model's ability to recall information over long distances. However, the introduction of Mamba, a new SSM architecture, has expanded the possibilities for balancing recall and memory usage. This led us to question whether simpler models could also achieve a similar balance. We experimented with two straightforward techniques: sliding window attention and a linear approximation of softmax for attention. Our experiments in language modeling and synthetic recall tasks indicated that neither approach alone was sufficient to effectively navigate the trade-off between recall and memory usage. Specifically, linear attention struggled with associative recall tasks due to its lack of precision for local token adjustments and comparisons. Meanwhile, the range of associative recall achievable with sliding window attention was limited by the size of the windows, and increasing the window size resulted in a linear increase in memory size, which in turn affected speed during parallel training and inference. To address these challenges, we combined sliding window attention and linear attention into a single architecture, which we named BASED. This combination allowed BASED to expand the possibilities for balancing recall and memory usage. We hypothesized that the large memory capacity of linear attention could facilitate modeling of long-range interactions between tokens, while sliding window attention could handle precise local adjustments necessary for associative recall. To ensure that BASED could compete with state-of-the-art attention and recurrent models in terms of speed and throughput, we implemented several input-output-aware optimizations. Despite theoretical advantages, linear attention often falls short in speed compared to well-optimized attention mechanisms. In BASED, we utilized a second-order Taylor approximation of softmax for the linear attention feature map. This approach, while theoretically more efficient, required careful optimization to be competitive in real-world scenarios in terms of speed and memory usage. We also leveraged tensor cores, specialized hardware units found in modern GPUs, to optimize sliding window attention. By choosing window sizes based on hardware characteristics, we were able to minimize latency associated with launching tensor core operations. Our experiments demonstrated that our model not only competes in quality with advanced transformer models and other high-performing architectures but also surpasses previous models in associative recall tasks and in efficiency, achieving higher throughput in generation tasks. In summary, our work provides new insights into the trade-offs between recall capabilities and memory usage in language models, introduces a novel architecture that balances these aspects effectively, and offers practical optimizations to enhance real-world performance. Section Summary. In this section, we explore the impact of different sequence mixers, such as attention and convolutions, on the quality and efficiency of language models. We investigate the trade-off between high recall and high throughput models, introducing a new architecture called BASED that combines sliding window attention and linear attention to expand the Pareto frontier. By optimizing memory usage and introducing hardware-efficient algorithms, BASED outperforms existing models in recall-intensive tasks and enables significantly higher throughput during generation. Section: Preliminaries and related work. In this section, we delve into the most relevant previous studies and expand upon them in a detailed discussion found in the appendix under Extended Related Work. The concept of attention, particularly spotlighted by the advent of transformers, has become a cornerstone in language modeling. This mechanism processes inputs of a certain length and dimension, and generates outputs by applying a softmax function over certain projections, specifically in scenarios where the projections are learnable matrices. Despite its proficiency in recall and its training efficiency, thanks to its ability to be parallelized on GPUs and its relatively low memory footprint with recent advancements, attention is still notably resource-intensive during the generation phase. For each new output, a significant number of operations are required over an expanding cache of prior data, leading to increased memory usage and reduced throughput for longer sequences. To address these challenges, various efforts have been made to enhance the efficiency of attention mechanisms without compromising their effectiveness. Sparse attentions, for instance, aim to lessen both the computational time and memory demands by focusing only on certain patterns or local areas. Although these have been incorporated into large language models, they sometimes fall short of full attention capabilities due to their inability to capture dense interactions or because they still rely on large window sizes, which can lead to inefficiency. On the other hand, linear attentions substitute the softmax function with alternative kernel functions, thereby eliminating certain computational steps in favor of dot products between feature maps. This approach allows for attention computations to be carried out more quickly and with less memory usage. Moreover, it supports a recurrent approach that requires constant memory and reduces the time needed for processing each token. However, the feature maps used in current linear attention models either do not reach the recall performance of standard attention or are costly to compute. In practice, linear attentions have not yet achieved faster processing times or lower memory usage compared to the latest standard attention models. Furthermore, we explore alternatives to attention, such as sequence mixers that do not rely on attention mechanisms, including state space models, gated convolutions, and input-dependent recurrences. These alternatives have shown promise in matching the performance of attention in terms of overall perplexity. However, further investigation suggests they might not perform as well as transformers in specific tasks like recall and in-context learning. We also introduce a critical trade-off between a model's memory usage during inference, that is, the size of its recurrent state, and its ability to perform recall tasks. Through a combination of experiments with synthetic data and theoretical analysis, we demonstrate this trade-off. Specifically, we use a synthetic task known as multi-query associative recall to illustrate how varying a model's recurrent state size impacts its recall accuracy. Our experiments, which include a variety of sequence mixers such as attention, sliding window attention, and others, reveal a clear trade-off. Larger recurrent state sizes generally lead to better recall. However, performance varies across different architectures even with the same recurrent state size, indicating that some models are more efficient in utilizing limited memory to achieve high recall. Our findings underscore the importance of designing sequence mixers that can push the boundaries of this trade-off, allowing for more efficient models without sacrificing recall capacity. By adjusting hyperparameters that influence the model state size, we can navigate the trade-off between efficiency and recall capability, aiming to expand the frontier beyond existing models like Mamba. This exploration not only highlights the inherent challenges in optimizing memory and recall but also points toward potential pathways for developing more efficient and capable models in the future. Section Summary. In this section, we delve into the preliminary concepts and related work surrounding attention mechanisms in language modeling. We explore how various approaches, such as sparse attentions and linear attentions, aim to enhance the efficiency of attention mechanisms while maintaining quality. Additionally, we investigate the trade-off between a model's memory consumption and its ability to perform recall, showcasing how different architecture classes impact this balance through empirical studies and theoretical analyses. Section: Theoretical Analysis. In this section, we delve into a theoretical examination that sheds light on the observations we've made through our experiments. Initially, we draw upon communication complexity theory to demonstrate that the ability of any causal model, such as Mamba or attention, to recall information is limited by the size of its recurrent state. This finding supports the idea that the trade-off we've noticed is a fundamental aspect of these models, rather than a mere consequence of their design. We then turn our attention to gated convolutions, which are a wide-ranging category of architectures that incorporate both gating mechanisms and convolution operations, including examples like H3, Hyena, and RWKVV4. To advance our theoretical understanding of these architectures, we build on previous work that established a standard form of gated convolution capable of emulating any design based on gating and convolution. Our analysis reveals that this standard form cannot address certain problems within a fixed number of layers, unlike attention mechanisms which can handle these issues efficiently in a similar setup. This distinction helps explain why architectures based on gated convolutions fall short of the performance benchmarks set by newer models. Furthermore, we demonstrate that it's possible to approximate linear attention, which is at the core of the based architecture, using the standard gated convolution form, albeit with an increase in the number of layers required. This comparison highlights the relative efficiency of linear attention compared to gated convolution architectures. Moving on to the based architecture, our goal in creating this design was to explore how we could effectively navigate the trade-offs between memory usage and recall capability using well-established architectural elements. Softmax attention is known for its strong recall abilities, but its reliance on a KV cache that grows with the sequence length places it in a less desirable position in terms of memory efficiency. We investigated two strategies to limit the size of the attention's recurrent state: linear attention and sliding window attention. Linear attention, which does away with the softmax operation, doesn't increase in size with longer sequences and allows for adjustments through simple parameter changes. Sliding window attention, on the other hand, restricts the recurrent state to the size of the window used. Our experiments, which included both real-world language modeling and synthetic associative recall tasks, indicated that neither approach on its own could achieve the optimal balance we were seeking. Linear attention struggled with tasks requiring precise local adjustments, while sliding window attention was limited by the window size, affecting its ability to recall information over longer distances. By combining these two approaches, applying linear attention globally and softmax attention locally within small windows, we were able to significantly improve recall accuracy with minimal impact on latency. In the context of linear attention, we approximated softmax attention using linear feature maps, which allowed us to maintain interactions between all tokens while keeping the recurrent state size manageable. We selected a specific feature map that enabled us to rewrite the softmax attention formula in a way that was both time and space efficient. This approach ensured that the size of the recurrent state remained constant during the generation process. To approximate a particular mathematical function, we employed a feature map based on the Taylor series, choosing parameters that balanced efficiency and recall capacity. While selecting a feature map with certain characteristics could lead to a more efficient but less capable linear attention mechanism, we found that adjusting the dimensions of queries and keys allowed us to fine-tune the size of the recurrent state and navigate the memory recall trade-off effectively. Our analysis of various feature maps, including the Taylor series, POS-ELU, ReLU, and others, revealed that the Taylor series feature map offered a favorable balance of recall capacity and parameter efficiency, informing our decision to use it in our architecture. Section Summary. Theoretical Analysis. Our theoretical analysis delves into the recall capacity limitations of causal models, showcasing that the size of the recurrent state bounds their recall capacity. Additionally, we explore gated convolutions and demonstrate that attention outperforms them in solving certain tasks with fewer layers. This sheds light on why newer architectures surpass gated convolution models. In this section, we introduce BASED. We aim to balance memory and recall trade-off by combining linear attention and sliding window attention to navigate the Pareto frontier effectively. Linear attention, by approximating softmax attention, maintains global token interactions while constraining the recurrent state size, leading to efficient recall capacity. Section. Local exact attention with tensor core sliding windows. In this section, we delve into the concept of local exact attention with tensor core sliding windows. To effectively capture the intricate details of local interactions, we employ a technique that uses sliding window attention. This method involves setting the window sizes to small multiples of 15, and can accommodate up to 64 tokens. Drawing inspiration from previous causal implementations, for a window size of 99, each query is designed to only consider passed keys. This approach allows us to achieve linear scaling in terms of time and space complexity relative to the sequence length, while maintaining a constant memory footprint for generation through the use of a cache size to the window. However, our method, which we refer to as BASED, diverges from previous implementations by utilizing smaller window sizes of either 15 or 16. This choice is strategic, aimed at maximizing the performance benefits offered by modern GPUs. In a specific section on efficiency, we discuss how this approach, which we've termed Tensor Core Aware Window or TCWINDOW, significantly reduces latency compared to the windows used in contemporary large language models, such as Mistral 7B. Although the smaller window sizes in TCWINDOW facilitate rapid and precise attention mechanisms, they pose a challenge for modeling long-range interactions. To match the receptive field achieved by a single layer of Mistral's sliding window attention, BASED would require 16 layers. When we control for model depth and sequence length, we observe a linear decrease in associative recall accuracy with smaller window sizes. Nevertheless, BASED overcomes this limitation in long-range modeling through the implementation of global linear attention. We further elaborate on the architectural nuances of BASED in an appendix and detail the hybrid layer structure used in our experiments. Additionally, we present a comparative analysis of architectural choices and assess the overall performance and efficiency of BASED in a results section. Focusing on the efficiency of our approach, we acknowledge that a straightforward implementation might lag behind the most efficient standard attention mechanisms in terms of speed, as shown in our throughput analysis. This inefficiency stems from the need for extensive high-latency memory transactions. We begin by outlining the basics of GPU execution models and memory hierarchies, then introduce our baseline and hardware-optimized algorithms for both linear and sliding window attention. In the context of GPUs, operations are executed across thousands of parallel threads. NVIDIA's architecture, for example, organizes these threads into blocks, which are then divided into warps of 32 threads each, assigned to specific cores. These threads must load inputs into their registers to compute and then write the outputs, with the read-write cycle constituting the I/O cost. Depending on whether the bottleneck is data loading or computation, operations can be classified as either memory or compute-bound. Our goal in designing EO-aware algorithms is to leverage two key features of modern GPUs: the high speeds of tensor core units for matrix multiplication compared to non-matrix multiply cores, and the memory hierarchy that prioritizes access speed based on the data's proximity to the processor. For instance, the NVIDIA 80GB A100 GPU features a memory hierarchy that includes 80 GB of HBM with 2 TB per second bandwidth, complemented by 80 megabytes of L2 cache, 192 kilobytes of L1 cache, shared memory, and 256 kilobytes of register file per streaming multiprocessor. It's crucial for threads to utilize shared memory for inter-thread communication within a block, aiming to minimize read-write times by processing data in fast memory before moving it to slower storage. In the realm of Taylor exponential linear attention, despite theoretical advantages, linear attention methods have often fallen short of the efficiency benchmarks set by optimized softmax attention mechanisms in real-world applications. We introduce hardware-aware algorithms designed to enhance the efficiency of Taylor linear attention, focusing on two key operations: prefill, which involves processing the prompt during generation or training, and next token prediction, which also entails updating the recurrent hidden state. For clarity, we define specific terms related to batch size, number of heads, head dimension, sequence length, and feature dimension, as outlined in our architecture section. Further details on our EO-aware algorithms are provided in an appendix. Section Summary. In this section, we introduce an efficient implementation strategy for our model, focusing on optimizing GPU execution and memory usage. By leveraging GPU streaming multiprocessors and exploiting the fast matrix multiply units, we design hardware-aware algorithms to reduce I/O costs and enhance computational efficiency. Our approach considers the memory hierarchy of modern GPUs, aiming to minimize data movement between fast and slow memory tiers for improved performance. Section: Forward Pass, Generation Prefill. In this section, we delve into the process of generating prefill during the forward pass and the baseline implementation of this process. Initially, our straightforward approach, as detailed in Appendix 1, involves producing feature maps, computing and materializing a large hidden state, and then performing a causal dot product between specific elements. Previous studies have introduced efficient CUDA kernels for linear attention that effectively carry out the causal dot product. These kernels work by parallelizing the computation across different heads and batches, loading segments of data into SRAM, updating the ongoing state within SRAM, and finally, transferring the result to HBM. When we ignore the input and output projections in the linear attention layer, this method requires a certain amount of bytes to write the featurized data to HBM and additional bytes for reading and writing during the causal dot product phase. Throughout this computation, a significant amount of data is transferred between thread registers and SRAM to update the output and state, utilizing a bandwidth of 19 terabytes per second. To enhance efficiency, our algorithm performs both the feature map creation and the causal dot product within fast memory. We detail our comprehensive algorithm and discuss its process, which starts by parallelizing over the batch and head dimensions, given that computations for each head in each batch are independent. We then focus on three specific terms in the linear attention output, which correspond to the terms in a certain order Taylor polynomial for the exponential function. As we process a sequence, we also consider these terms in relation to the cumulative state. For a given segment of data, we load the necessary tiles into fast memory and update the ongoing state and output for each term. By loading these tiles into the register file and fusing operations, we compute the causal dot product directly in the register, only writing to SRAM to synchronize the cumulative state across parallel warps. This is because register memory is specific to each warp, preventing threads in one warp from accessing registers of a thread in a different warp. In terms of input-output cost, our procedure significantly reduces the bytes required for reading and writing between HBM and SRAM, thereby avoiding substantial data movement. Moreover, by performing computations in register, we further reduce the data movement from SRAM to register memory. When predicting the next token, an essential aspect to consider is how to efficiently update the recurrent state at each time step. The most resource-intensive operation in this phase is computing the outer product between projected hidden states. This operation not only requires a considerable amount of computation and space but also involves summing the result with another term to produce the final output. We propose an input-output-aware algorithm for these state updates, which minimizes the data movement between HBM and SRAM required to load the projections. Lastly, we discuss the rationale behind choosing a specific window size for our model. Unlike sliding window models that use large window sizes, our model selects a window size based on hardware specifications, specifically the operation of GPU tensor cores on certain tile sizes. This consideration ensures sufficient occupancy to conceal the latency of tensor core units. We distinguish our approach by referring to it as a specific model and utilize the flash attention sliding window implementation during training. We also provide an input-output aware algorithm for next token prediction and include end-to-end benchmarks and micro-benchmarks for our model, comparing it against baseline implementations. Section Summary. In this section, we present an improved algorithm for efficiently computing feature maps and causal dot products in fast memory, reducing data movement and improving performance. By parallelizing computations over batch and head dimensions and optimizing memory usage, we achieve significant reductions in data movement and enhance computational efficiency. Our approach minimizes data transfers between high bandwidth memory, HBM, and fast memory, leading to improved next token prediction performance and overall algorithm efficiency. Section: Results. In this section, we share our findings on several key points. Firstly, when it comes to language modeling as a whole, we put various architectures to the test by starting from scratch on the pile and using standard benchmarks from the LM-eval harness. We discovered that our model, referred to here as 7-number-7, either matches or surpasses the performance of the most advanced sub-quadratic architectures, such as Mamba, across these tests. Regarding language modeling recall, 7-number-7 narrows the performance gap with attention mechanisms on the particularly tough associative recall part of the real-world pile language modeling corpus. This is a significant achievement, as it outdoes previous sub-quadratic architectures. We then applied these pre-trained models in a zero-shot manner to a collection of recall-demanding tasks, like information extraction and question answering, and found that BAST consistently outperformed other efficient architectures that have similar processing speeds. When we look at generation throughput, our approach to recurrent generation in BAST, which is mindful of input-output operations, results in speed improvements of up to 138 times compared to FLASHATTENTION2 and Mamba for initial sequence generation at a length of 139, and achieves up to 36 times higher throughput than FLASHATTENTION2 when generating 10 tokens at a batch size of 140. We also conducted ablations on 4 crucial design choices and hyperparameters: the feature map, the feature dimension, the use of a local sliding window softmax, and the implementation of short-gated convolutions. The outcomes of these ablations are detailed in our results section. In terms of baselines, we made comparisons with key models previously established in the field. This includes the Transformer, GPT architecture, and Transformer++, Llama architecture, which incorporates rotary encodings and gated linear units. We also looked at an early class of efficient architectures that utilize gating and long convolution primitives, including Hyena, RWKV, and H3. Lastly, we compared our results with recent top-performing architectures that use input-dependent sequence aggregation to enhance quality over the long convolution models, such as Mamba and gated linear attention. For language modeling benchmarks, we pre-trained language models from the ground up at 2 different parameter scales, 355 million and 1.3 billion parameters, on the pile. Each model was exposed to the same 10 billion tokens of pre-training data in the same sequence. The data from the pile was tokenized using the GPT-2 BPE tokenizer. We measured perplexity on the pile and reported these results, with further experimental details available in the appendix on pre-training. We also evaluated the pre-trained models on the standard LM-eval harness, following the standard protocol for our baselines. A detailed breakdown of tasks and metrics is available in the appendix on downstream evaluations. In both pre-training and on the LM-eval harness, 7-number-7 consistently held its own against the strongest Transformer++ and Mamba baselines. For recall and in-context learning evaluations, we tested our pre-trained models on a set of in-context learning tasks chosen to assess downstream recall ability. These tasks are categorized into real-world associative recall, information extraction from semi-structured and unstructured documents, and question answering from in-context passages. Here, number 7 outperformed the baseline sub-quadratic architectures across these evaluations, closing the gap to Transformer++. Lastly, to explore the capabilities of number 7 beyond natural English language, we evaluated each architecture's ability to predict the next token in DNA sequences. We tested the architectures on the HG38 human genome benchmark at various sequence lengths previously used in architecture evaluations. The DNA tasks used a byte-level tokenizer with a vocabulary consisting of characters representing nucleotide bases. We found that number 7 competes well with state-of-the-art architectures across the evaluated sequence lengths. Further evaluations on downstream DNA classification tasks are discussed in the appendix on downstream evaluations. Section Summary. In this section, we present results on various claims related to language modeling, including performance on pre-training from scratch, recall tasks, and generation throughput. We compare our model to strong baselines like Transformer++ and Mamba, showing competitive results across different benchmarks and tasks. Additionally, we evaluate the model's performance on DNA next token prediction tasks, demonstrating competitiveness with state-of-the-art architectures across different sequence lengths. Section: Efficiency Benchmarks. In this section, we discuss how we evaluated the performance of our model, both with and without our newly developed EO-aware algorithms. We looked at two key stages: the initial setup or prefill stage and the stage where the model predicts the next token. To do this, we conducted experiments using an H100 NVIDIA GPU and repeated these tests 145 times to ensure accuracy. The results of these tests are illustrated in a figure in our paper. When we compare our model's efficiency using our effective implementation, we find that our model completes the prefill stage 56% faster than FLASHATTENTION2 and 44% faster than Mamba when dealing with sequences of 139 characters and models with 1.3 billion parameters. For smaller models with 360 million parameters, our model is 28% faster than FLASHATTENTION2 and 76% faster than Mamba. In terms of generating the next token without prefill, our model processes 36 more tokens per second than the highly optimized FLASHATTENTION2 and nearly matches the throughput of the recurrent Mamba architecture with a batch size of 140 and 1.3 billion parameters. Specifically, our throughput is 98% higher compared to FLASHATTENTION2 and 118% higher compared to Mamba for models with 360 million parameters. All these benchmarks were conducted on a single NVIDIA H100 GPU, utilizing CUDA cache graphs during the next token prediction stage. Additionally, we included results for a baseline version of our model that uses a popular fast transformers CUDA kernel to compute the causal dot product, which is a common operation in linear attention models. Our custom kernel significantly enhances efficiency. Furthermore, since our architecture is a hybrid, we also provide detailed benchmarks for the individual EO-aware components of our model, comparing them to key baseline implementations. In terms of model quality, our goal with BASED was to evaluate the simplest possible linear attention model that still delivers strong performance. To understand how different design choices affect the model, we experimented with various configurations, including the choice of feature map, the dimension of features for the Taylor map, and the use of sliding windows and convolutions. These experiments were conducted using the pile corpus, maintaining the same token count and data ordering as previous tests. For feature map comparisons, we looked at the CUS former and performers feature maps, known for their effectiveness in linear attention models. We also tested a baseline that increases the state size with learned projections and uses CUS former, to see how it compares with the larger state size of the Taylor map. We found that increasing the state size makes CUS former increasingly competitive, though it also requires a larger overall parameter count due to the learned projections, unlike the Taylor map. When we fixed the feature map to the Taylor map and varied the feature dimension, we observed that larger dimensions improve model quality, though the benefits diminish as the dimension increases. We also noted that removing convolutions or sliding window attention reduces model quality. However, adding either convolutions or sliding window attention improves performance on associative recall tasks. Moreover, increasing the window size further enhances quality, but the improvements are marginal beyond a certain point. Through these experiments, we aim to identify the most efficient and effective configurations for our model, ensuring it not only performs well but also operates efficiently on hardware like the NVIDIA H100 GPU.